Good morning, everybody. Thank you very much for coming along today. If you haven't met me, my name is Nancy Ganaway and I'm the Future Farming Systems Development Officer for the Climate Resilience Task Force. We love how you guys have been enjoying our morning teas and coming along, and for everybody in the room. It is my privilege to present to you Dr. Ian Foster, Senior Climatologist here at the department. I've been working with Ian on and off. I had the privilege for a good 20 years now. Ian began with the department in 1989 as a climatologist, and his experience includes modelling atmospheric pollutants. He was a founding member of the Indian Pacific Climate Initiative in 1997, and he is responsible for more than 197 with more planned automatic weather stations which are providing seasonal climate information to inform business decision making that's both strategic and tactical within the season and across the year. So he's a very important gentleman and someone we're lucky to have here. He also heads up liaison between our climatologists and our organisation with CSIRO and the Bureau of Meteorology, and provide climate monitoring services for a range of climate events. Now, as someone who used to have the privilege of sitting in a weekly meeting with Ian, I can tell you that he is statistically more accurate than the Bureau of Meteorology. We used to have bets about this from week to week, and you really want to know what's happening with the weather, talk to Ian. And one of the most profound things that Ian has ever said to me about the future of global warming and the changes that it might have to us and how we live is that a possible future, if we don't get on top of global warming, is if we want to have dairy, cheese products, ice cream, those sorts of things, that we may one day have to have big refrigerated or air-conditioned sheds for our cows so that they can have an environment where they can produce those products that we love. So if you like cheese, we've got to get our greenhouse gas emissions down. So I'll hand you over to Ian.
Thank you all for your attendance and interest. I'm planning in this one to look at more of the physical science behind the greenhouse effect and why certain gases are important. There will be a little bit of stuff to do with the latest projections, but it's not primarily about that. It's more about understanding where we come from in terms of the physical science with it. And to that end, I'll start with this complicated graph of the global energy budget. This is actually from NASA. So these are measurements for the last 10 years, global measurements. The units are watts per square metre. Now, there's lots of versions of these sorts of things around. They're very complicated. Essentially, it's saying in the top of the atmosphere, the yellow arrows refer to the shortwave radiation coming from the sun. So Planck's radiation law says the sun's hot, and so it transmits at shortwave radiation. So that's the visible light that we see. There's no surprise that most life on Earth uses visible light to either see things or to get its energy from. Now, the input from the sun does vary. It's not constant. It varies with the Earth's orbit around the sun. Its own luminosity changes as well over its lifetime. So, but for our intents and purposes, it's more or less constant. It does vary a bit. Approximately half of it that enters the atmosphere at the top makes it to the ground. Other bits are reflected or scattered by clouds or aerosols. Some are absorbed by the atmosphere as well. At the top of the atmosphere, what comes in, essentially, this bit's got to be balanced by the stuff that goes out. Otherwise, if you get any imbalance, you'll either warm the planet up or cool it down. There's lots of examples, not only around our own solar system, of this sort of stuff. So it's a nigh on universal principle. At the surface, we've got a series of incoming fluxes, which is from the sun, obviously. The bit that's not really appreciated, that it's actually the downwelling infrared from the atmosphere is actually a greater component. The point is this exists across the whole globe 24/7, whereas this, of course, only exists on the part of the sun or the part of the planet, which are sunlit. So it sounds counterintuitive, but the budget at the bottom, what comes in is absorbed, has then got to be got rid of and the major way it gets rid of is by radiation. Because the Earth's effective temperature is much less than the sun, it radiates at longer wavelengths. So there's fundamental radiation laws by Max Planck and the others, dictated in the 1800s, that describe this. So if anybody will be radiating, everything within this room is radiating at the moment. But what temperature it is dictates what wavelengths it radiates at. So what gets absorbed by the Earth's surface gets radiated away again. We also have the right, the surface gets rid of energy through convection, that's thermals on a clear day from hot surfaces, and also through latent heat evaporation. So that's evaporated water. So that bit there tucked in the corner is weather. Now, the atmosphere plays a key role in the middle because that's sort of like the middleman intercepting the radiation and re-radiating it both upwards and downwards. So various molecules will absorb the long wave in particular. The re-radiation is isotropic, goes in all directions, which means there's a downwelling component and an upwelling component. So that's why the atmosphere is so important. If you didn't have that, then the effective Earth's temperature would be much, much less than it is. So as far as we're concerned, the atmosphere is very important, A, because it contains weather, contains oxygen, but also by the presence of some of these greenhouse gases, it actually makes the surface temperature some 30 degrees warmer than if we didn't have them. So it's actually quite a useful thing. But it's just to note that this is all a very dynamic system. These fluxes are happening instantaneously. So these might be global averages for 10 years or so, but they're changing instantaneously. So it's not a static thing, and it's sort of like a dynamic equilibrium. As one bit changes, the other bits will change in response to it. So there's a lot of moving parts here. The other part of it here I'm trying to show is the top two curves are the emission spectra as defined by Planck's law. Now, they're not at the same scale. The effective Earth temperature is much less than the sun, so its actual emissions intensity is much, much less. So the red ones is the right-hand scale. Now, Planck's law says that for a body at 6,000 degrees Kelvin, it'll emit at about 0.5, 0.6 of a micron. So that's visible light. That's the bit that we can see. Plants absorb at that, so that's pretty logical. But the Earth's temperature, the effective radiative temperature is much less, so it radiates itself at about 10 to 15 microns. So that's fundamental physics has shown this sort of displacement. Now, there's two key greenhouse gases, or by the word greenhouse gases, I mean things that absorb strongly in the infrared. One is water vapor and one is carbon dioxide. Now, this plot here is just their absorption spectrum, meaning if it's black, they absorb everything at that wavelength. So for water vapor, everything more than about 20 microns is completely opaque to it, just absorbs it all. There's this region here of around 10 microns and a few either side where the absorption from water vapor is low. So this is the so-called atmospheric window. There's some absorption bands of CO2 here. Now, these are smooth. The actual spectra are much more complicated, but these are just smooth to make it easy of viewing. So there's a big absorption band of CO2 that sits right in the middle of the emission from the planet. So it has a role to play there because of its interaction, the molecules' interaction with long-wave radiation. So it's got skin in the game, I guess, and that sort of thing. So that's the fundamental reason why radiation eventually gets out, but also why these gases have a role to play in increasing the downwelling radiation. Now, water vapor has a complicated role in that it can cool the atmosphere if it exists as clouds, that sort of thing. But if it exists as a vapor, such as this vapor within the room now, it's invisible to us, but it's absorbing infrared. So it's actually got a strong role, but its concentration is highly variable around the globe, whereas things like carbon dioxide are a well-mixed gas. Now, just a bit more looking at, chucked a few colours in. This is just a repeat of some of these absorption spectra. Ozone's a strong absorbing gas, so this is the atmospheric, this is the long-wave radiation from before, but most of the ozone's in the stratosphere. So when it absorbs and re-emits, it goes out to space preferentially rather than coming down to the surface. There's the CO2 spectrum as before. That's that one there. The blue one's water vapor. You've got nitrous oxide, which has a finger in the pie. It's got some absorption bands in the infrared, and also methane. So these gases, that's why they're coming up and people are talking about them, because their absorption spectra is right in this band where the planet's trying to re-emit back up to space. So it has a key role to play. So there's two bits with those. It's how strongly they absorb the radiation, but also the concentration of the gases. which is what this plot's trying to get. This is from this is just a pie chart, not of all the gases in the atmosphere, mercifully. Might be like that, not quite on Venus, but some of the planets have that. Carbon dioxide is the most significant gas, partially because of its concentration. It's actually now exceeded that, and also because of its particular location in the emission spectrum. Methane, on a molecule per molecule basis, is a much stronger absorber, but it's not as common within the atmosphere. But it's still, in terms of this relative impact, is the next most important gas. And you can then raffle some of the others. You've got nitrous oxide. The halocarbons, that's the CFCs, that are very strong absorbing gases, but they're not in very high concentrations. So again, it still comes down to, of all of these gases, the big two tend to be from basic physics. It's carbon dioxide and methane. Now, the IPCC has done some work, and this is in their latest assessment report, where they've looked at the contribution of these various, what they call drivers, to heating or cooling across the planet. And the first bar there just simply shows the overall warming since the period 1850 to 1900 to the latter part of the, or to the early part of the 21st century. So globally, in rough figures, there's a degree or so of warming of the planet. So the next one here, they've now done some attribution in terms of the greenhouse gases. So there's potentially, this one here's the well mixed. The second bar here is well mixed. This is the net effect. But note the blue bar. So blue means it maybe have cooled the atmosphere a bit. That's actually from aerosols, those sorts of things. And you can raffle the other effects of sort of volcanicity and variability of solar radiation within this time periods. Not much to worry about. Even though on annual basis, volcanic activities can make a difference, over this time period, it hasn't been much of an effect. They further expand this further, looking at, to take this bit, so that's the aggregated warming from the greenhouse gases. The big one, again, is carbon dioxide with methane. So that's still the big two. There's a bit of a, smaller kicks for nitrous oxide and the other gases. That's cooling from nitrous oxides, which is a pollutant. Sulfur dioxide, which is one of the main drivers of aerosols. So these blue bits tend to cool it a bit. There's a bit of warming from other organic compounds, but these tend to be the biggest two. And it tails off here. Black carbon, that's soot and stuff that can sit on snow, that can act as a bit of warming. This bit here, there's a little blue bar to the right. That's the effect of increasing the reflectance of the surface from changes in land use and cover. And we know that locally that can be very, very significant. If you change a land surface from vegetation to urban, you change energy balance. So it makes a big difference there. But globally, it's much less significant because most of the planet is water. So that's only the terrestrial-based stuff. So the IPCC's done this sort of stuff, and they still come down to the big two in terms of driving this warming, still seem to be these two gases, carbon dioxide and methane. Now, we know carbon dioxide has varied a lot in the historical past. The chart on the left is from the ice cores in Antarctica, going back approximately 800,000 years. And you probably see these, you recognise these patterns of the ice ages and interglacials, ice ages, interglacials. This sort of thing is essentially driven by variations in Earth's orbit. These are the Milankovitch cycles. It kicks things off. But with CO2 and methane acting as amplifiers to this process. So it's bumped up and down. We know that. It does it all by itself. We know as well on the really long geological timescales, CO2 has been even higher. But as far as the relatively recent history, it's very much driven by these glacials, ice ages, interglacials. And this is the most recent one here that we're sitting in. But it tends to not exceed 300 parts per million. This plot on the right is a more recent thing going back a couple of thousand years. So you're seeing it's been bumping along about 280 parts per million. And then in the middle of the 19th century, coming from population and industrialisation, is just shot up like crazy. So it's now exceeded 400. So that's certainly the highest amount we've seen in a million years or so. So it's not so much what the amount is, but it's the rate of change. This is a very, very rapid change. These things would still take thousands of years to change. This has happened in 100 years or so. So a lot of the issues with this stuff is not so much what the CO2 concentration is, but just how rapidly it's changed. And all those other radiation components are then changing rapidly in response to this. So it's a very dynamic system. This is just showing the source of the various emissions of carbon from 1850 on the left. These are just the annual estimates from the Global Carbon Project. The bit above the line is the emissions from the grey bit, fossil fuel emissions, so that's industrialisation, land use changes. Below the line shows sinks into the ocean, which is this bit, at land surfaces, which is absorbing of carbon into plant surfaces. But the atmosphere is the residual. So this bit's about 40 odd gigatons a year. The combined efforts of the land and the oceans takes out about half that, which means the residual stays in the atmosphere. So that's that bit there. The plot on the right is just the cumulative emissions since that time, so it's a bit more smooth. And if you eyeball that curve, you see it looks as though it's accelerating. It certainly has been. So it hasn't been a slow decline or slow increase. It's really been shooting up pretty quickly. So that's the bit that we see in the atmosphere. So total emissions are driving it all. And that's largely, this grey bit here, that's largely what they call fossil fuel emissions. That's industrialisation. So there's nowhere else for it to go, basically, because it's not been taken out fast enough. And this has got to do, again, with the issue of rates of change. It's getting into the atmosphere at a much greater rate than the land surfaces can take it out. Now, the IPCC has done some attribution experiments. This is now similar to what we'd seen before, but this is the global temperatures. Now, this is reconstructed from ice cores, and that's the observed. So this is the so-called, it's been referred to as a hockey stick graph. Looks like a stick stuck on the ground on the side. So we've seen this rapid warming from 1850. So there've been lots of bumping about, up and down, a lot of uncertainty with there. If anything, a general cooling. So the year 1500 was a so-called Maunder minimum, which was a sunspot year, when you actually had the Thames, for example, in England froze over. So you have had warmer periods and cooler periods in the past, but since the 1850s, it's really warmed pretty quickly. So it's just, again, the shape of the curve, that's the real issue. Now, they've done attribution experiments, in this case where they've simulated with global climate models the global climate since 1850, and this is the temperature. The black lines are the reconstructed observed temperatures. Now, in the first set of experiments, they kept CO2 constant. So, and they just looked at the known occurrences of variation, solar radiation, volcanoes, that sort of stuff, the so-called natural forces that were seen before in some of those other budgets. And so it explained pretty well the early part of the record, but fails to explain from the late 20th century the warming. The second set of experiments is where they keep all the natural forcing, but you just let CO2 rise according to the observations. So not only can you explain the early bit of the record, you can now explain the latter bit of the record. So at least within the climate modelling environment, at least, the addition of CO2 seems to be a strong explainer for the observed trends we've been seeing. The other bit that comes out of that is that it's really not until the late 20th century that you start to see the greenhouse signal emerging from the noise of natural variability, meaning prior to that, it would have been a largely theoretical thing. The observations wouldn't have been supporting your case, but since there, you've now seen the greenhouse signal is actually emerging from the noise of variability. So that's fairly important. So these things have been done. The various IPCC reports have had goes at this. This is just from the latest one, the 6th assessment report. And the same proposition pretty much changes, pretty much stays the same, that the CO2 rise seems to be the major driver for this temperature trend. Now, they then run it through, you've probably seen various versions of this, running through, okay, well, what's going to happen to future emissions? So this is the idea of the emission scenarios. They keep changing the name. The previous report, they were called RCPs, Representative Concentration Pathways. They're now called Shared Socio-Economic Pathways. So essentially, they're combined stories of population, technology, energy use, behaviour change. And they range between the options of either a very continuous large emission of CO2 gases composed of various policy decisions which constrain it. Now, the numbers refer to the greenhouse forcing in the year 2100 in watts per square metre. So that would mean over the total of the globe, the forcing of these gases would be 8.5 watts per square metre. Just for reference, the current forcing is about 2.7 watts per square metre. So you get more than a doubling of that. So that's the radiative forcing. And going back to the first slide, that means everything else changes in response to it. So you have various other options. If we do a little bit, we do a bit more, or we act very aggressively to constrain things. And that's the idea of these sorts of policy choices, to try and constrain the warming to within 2 degrees or so. Now, there's a few things that come out of this graph. Firstly, any of these policies have got to be adhered to in perpetuity. So it's not as though you do a bit and then stop it and then start it up again later. For these two options here, we have very much constrained the emissions growth and pretty much limited. This means it's a multi-decadal requirement. You do have to do that pretty much forever. A couple of other things that come out of this is that it's not until the latter part of this century that you really see the difference between these emissions policies in terms of what the global temperature does. So this is a knotty problem from a few sorts of things. It means that most of the policymakers and parliaments making decisions at this time of year, this sort of thing is well beyond the life of any of the parliaments. But also by the time these greenhouse chickens come home to roost, that is, you know what the outcome of these policies might be, the bulk of the policymakers have been pushing up daisies for years. So they're not really going to see the results of decisions made now. It's very much an intergenerational issue in that what type of environment does the current generation wish to bequeath to future generations? So this is the sort of point that the likes of Greta Thunberg and contemporaries have picked up on. They say, hang on, you're handing us this sort of future without even asking us. So that's understandably why it seems an intergenerational issue, and it's why it's very sensitive in lots of areas. So there's lots of things that come out of this graph. So that means that even if we start working like crazy, it's not going to be for quite a few decades before you start to see any persistent difference. So again, with all the stats, you still got to have to be able to see the change for a while before you know you've made a difference. Now, we've been having this stuff for quite a while. This is some graphs we see. This is from the Greenhouse 88 conference, not 1888, 1988, which I attended. Graphics come a long way. This is the rainfall projections the Bureau of Met presented at that one. Now, they thought there were two potential likely cases, which they called scenario 1 and 2. The most likely case, I thought, was you simply get a southward shift of the weather systems in our part of the world, that the tropics would expand and the mid-latitude cold fronts would just move further southwards. The second one was a more complicated split flow thing, which I thought wasn't very likely. So with a more likely case, I would see in summer, which is this graph here, you'd see an increase in rain over the tropics. But interestingly, you'd also see it throughout the eastern parts of the grain belt and getting into the southern rangelands. And note the graphics there are pretty much hand-drawn. So a lot of this stuff is pretty much back of the envelope stuff. In winter, they said, look, you're looking at potentially 10% reduction in winter rain, increasing to a 20% reduction over the wetter regions. So this is at 2040. And those others they didn't really consider because they thought this wasn't very likely to happen. So this particular thing, as you're all probably pretty aware, has been verified pretty well. We have seen more summer rain, and we are seeing a trend of increasing summer rain in the south. Now, these are highly variable from year to year, but the trend exists. And we've certainly seen this trend. And to that end, I had a look at what was happening in our part of the world since 1988. And this is from the data comes from the Bureau of Met's website, where they averaged the rain over that blue region, which is essentially Dongara to Bremer Bay. So you can get the average June, July, August rain in those years since 1988, which are the blue bars. The lines, if you probably worked out for now, that's the decline if you've been cooling, or if you've been drying, sorry, 10% by 2040, or if you're doing it at 20%. So that's you'd have started at maybe the average there was 340 millimetres, and if it had been dried out at 10%, you'd be looking at about 300 millimetres as the average. We're currently sitting for that period then since 1989 at 287 millimetres. So according to that, we've actually dried out faster than those projections. So they weren't over-egging it. We've actually dried out a bit faster. And that black line, just the linear trend imposed upon that, makes it look a bit more dramatic because I've pinned it at 340 millimetres to start. So just from that, it implies, yep, we've actually, those original projections weren't overstating the case. Now, that's also been done in other areas. This is two charts taken from the State of the Climate Report, where you've got on the left for Victoria and for South West Region WA, slightly broader region than what I was showing. But this time they've gone back to 1950. And the blue lines are the actual rain for those periods and those years. The black line is a running average. So you see the rundown has been occurring in both of these areas. Started a bit earlier for us, but the Victorians are starting to catch up, as they usually do. They've always got to catch up. So We're always leading the way, of course. And the teal regions, no irony intended, but it's coincidental that it happens to be teal, with a range of the projections of the trends in rainfall. So some of the projections had little change, others had a more substantial change. So in general, the observations tend to be running along the bottom end of the range of these projections. That's the point of that one. So the projections in general, the ensemble of them might imply relatively little change, but the more or the stronger drying of these trends seems to be the one that's verifying best as opposed to the other ones. Now, the IPCC has been doing this sort of stuff for quite a while as well, and their headline reports have been changing in tone. In 1990, sorry, as you might have expected from the previous graphs, they've said, look, there's little evidence you can actually detect a change. They said the theory of greenhouse was well known by then. It's been known for a very, very long time. But they said there's little evidence we can actually detect it's actually kicking off. Then a few years later, they said, yeah, balance of evidence, you could discern it. So again, starting to lean a little bit, but not being very confident. A few years later, most of it over the last 100, so they're becoming more specific, chucking some more numbers in, is likely to have been due to that. And by likely, they defined it as more than 60% chance, 66% chance, meaning it's twice as likely that it would have been the case as not the case. A few years later, most of the observed increase is now very likely. So that's a 90+% confidence. So the confidence is going up, they're more expansive, and they're now saying, look, it's due to the anthropogenic greenhouse gas emissions. So they're really pinning down the attribution better. In the fifth assessment report, they now say it's extremely likely. So they've just run up to the top end of the range. That has been the dominant cause. So they're sort of being more emphatic. And the last one, that's pretty much saying, stop arguing. It's unequivocal. Now, these statements are, everyone's got to agree to it. They've got to mean the same things in many languages. So they'll spend days arguing over every word of these texts. So it's not as though it's just a bunch of greenies have written this down and handed it around. All the delegates pull over this thing in utterly inexhaustible energy to put in or remove any words. So it says that the delegates and the findings are becoming more and more certain and more convinced. So, and the language, it's significant that the language has become more emphatic. So that's the point of that sort of thing. They're saying, look, and they're also saying as well that you're just seeing it popping up everywhere. So they're now saying the signal in all these spheres are actually appearing and you're seeing it. Now, they also do, this is the plots you've probably seen before in different reports looking at changes in global rainfall. Now, I've just chosen this. This is from the IPCC's interactive website, so you can choose different emission scenarios, different years, sorts of things. I've just chosen it to give you the strongest colours, so it's not as though I'm trying to catastrophize, it just makes the image a bit easier to see. So this is about mid-century, the changes in rainfall relative to 1986 to 2005. The greeny bits where it's expected to be consistently wetter, the browny bits consistently drier, and the muted colours where there's no particular agreement amongst the models. On the website, there's a confidence overlay, a mask that you could apply to that, which I've removed just because it just makes it more complicated to see. So there's a few stories that come out of this that's been around for a while. In general, the tropics is expected to become more active as the hydrological cycle cranks up, but it's not zonally symmetric. There's some bits it does it more than others. The models are disagreeing in some areas, like north of Australia. There's not a lot of confidence in the trend. Some models wetter, some models drier. The very high latitudes, you tend to get more rainfall, partially from a shift in the weather systems, but also partially from the conversion of snow to liquid water precipitation. The other story to note that certainly for the southern hemisphere mid-latitudes, you had this persistent drying. So it means that we're not alone. We're in the same boat as South Africa, which is we're got close to their 0 day for water supplies in Cape Town the other year, but also off South America. And interestingly, the Mediterranean basin as well. The exact physical expression is different because the distribution of land and water is different between the two hemispheres. Interesting to see if in the tropical Atlantic you actually got decreased rainfall, because that would imply decreased incidence of hurricanes for the US. In no clear particular signal over Amazonia, ominous, depends on what they put in for clearing of the jungle, of course, but you've potentially got some drying coming out of there. Stronger signals over large areas of ocean. Now, there's a there's a confidence mask that gets applied onto that. And for these regions, there's a very high confidence that this trend is true. So this is really just to show that this particular pattern of a general wetting of the tropics, drying of the mid-latitudes and a wetting again of the poles has been around for a long time. And the latest models are sort of reinforcing that geographic pattern. So that sort of says that this is really a hemispheric response. It's not just happening in WA or in South Africa by itself. Now, this is on the report, the interactive website, you can get regional summaries. This is a slightly horrible looking graph, but this is for the Australian region. The columns are for maximum temperature, as you might expect, minimum temperature, total annual precipitation, and the right-hand one is for how wet it gets on the wettest day. That's what it's trying to say. The rows, they're scaled not in terms of years, but in terms of the amount of global warming. So 1.5 degrees, 2 degrees, not too much difference between these graphs, and then 4 degrees. So the idea really, rather than trying to pick over the numbers, is just to eyeball the changes in the colours. Clearly, it's scaled by temperature, so clearly these colours become much darker as warming progressive, especially with the T-maxes as well. Rainfall, as implied from the previous graph, it just keeps going. So this is, again, according to the models, if you get a 4-degree warming, the response of the southern hemisphere circulation not only spreads it from WA into maybe a tiny bit of Western Victoria, that sort of stuff. It really starts to kick into a lot of southeastern Australia. So this is a familiar story. You've seen that in lots of areas before. So there's nothing new about that, other than you certainly don't want to be occupying this space. The bit of interest implies, well, when it does rain, even though there may be big gaps or bigger gaps between the rain events, when it does rain, you may get much higher rainfall events. And that, of course, is very topical this year for Eastern Australia, where some of the component, at least of the very heavy rain they've been getting, is a greenhouse signal, where the atmosphere being warmer, it can hold more water vapour and therefore can precipitate it out a bit faster, which is what this is trying to say. And to that end, Carl Braganza at the Bureau of Met published this thing on the conversation a little while ago. And one of the graphs there is just interesting in that what they've calculated is since 1979, not only global temperature, which is the browny red colour, but this measure of precipitable water. And what that represents is that in an air column above you, if all of the water vapour that's there, because there's water vapour in this room now, if that was all precipitated out by whatever mechanism, how much water would you get? So it's a measure of the potential raininess of a particular area. And so they've seen, correlated with the rise in temperature, we've seen an increase in the precipitable water. Now, that doesn't mean that it will rain. It simply says if you get an event that can wring the water out, it's going to bucket down. That's effectively what that says. The equation behind that's an appallingly named Clausius-Clapeyron, which sounds like you should go to hospital for that. But it's really that describes as the change in vapor pressure or saturated vapor pressure with temperature. So it's been around for ages, it's well known, but it's a nonlinear equation. So as the temperature rises a bit, the ability of the atmosphere to absorb water vapor, or to hold it at least, goes up. So that's one of the other factors. So it may sound a bit counterintuitive in some parts of the world, even though you may get a declining annual rainfall, your flood risk may go up, because when it does rain, it absolutely buckets down. So, and that's seen in lots of other places in the world, where they're now seeing unprecedented amounts of rain being dropped and flood impacts, where people just haven't seen it before. Very much the case this year in Eastern Australia, Lismore, for example. So it's had some role to play in that stuff. But as you know, for those things, a lot of it's a preconditioning of the catchments from last year, and having 2 La Niñas in a row, you're always going to be looking down the barrel of a lot of floods. Now, just the last couple of slides. All of the previous things have just been very much big picture, arm waving sorts of things. And what people often want to know, well, what's that mean for my part of the world? And these are some plots or some maps that Meredith Guthrie has done from the Climate Services for Agriculture website. Now, what that's about is it downscales the climate projections. It looks at the suite of models, and you pick up a spot. You could pick Corrigan, or it could pick some lat long, and it'll give you seasonal rainfall estimates, not only what the observed stuff is, but snapshots at different years, but also for different emission scenarios. And in the plot on the left, she's chosen it for the year 2030, for April, October. Now, this is for the 30 years centred on 2030. So it means there's current years and future years with this one. That's the middling scenario. So that's not the worst by any means. So this is just the average range for that. The spatial pattern you'll all recognise. It's not dissimilar to what we know now. This bit here, the wetter regions certainly dried out more compared with history. We know that, and we know that we've got an emergence of some dry areas in the northeast. But the pattern there is what you'd expect. So you've got large areas here of 20 to 300 millimetres of rain. You crank it forward 20 odd years, the spatial pattern looks pretty much the same, but just to eyeball the colours. In particular, the wetter climates have decreased, they've become drier. These really wet climates of the far southwest corner have disappeared off the coast. So there's obvious implications for hydrology and biodiversity for that part of the world. But starting to sneak, maybe coming over the rabbit-proof fence, a more persistent aridity in the growing season. So there's still interannual variability on top of this stuff, so you may get fantastic years. But over time, it's just tending to push towards a dry sort of climate. Note, in some of the spots like the south coast, you have to eyeball it a bit. It hasn't changed very much. The dry bit does push towards the coast, and you start to see the emergence of some more crimping bits for say, the salmon gums area. So for the south coast, if you're looking maybe at Jerramungup Shire, it's not hugely dissimilar to what you're seeing now. But you're sitting down in the southwest looking at water sources, it's quite a different story. Or if you're some of the areas out here, maybe you haven't been experienced these sorts of years, well, these dry years are coming to a town near you. So it's just a useful tool that Meredith went through this thing, looked at the website umpteen million times to accumulate the points that she's been mapping. So she's got a whole set of these things, and that's presumably a subject for a future talk for Meredith to present some of this stuff. She's done a lot of work behind that. So this is just to illustrate that these tools are available for people to downscale it to their part of the world. So you don't have to try and squint and eyeball at some map. You can get the numbers for your part of the world. So that's a very useful tool. And finally, she also did it for temperatures. And in this case, she picked the period August to November. Late grain fill, as you might expect for a lot of these areas. But it's just looking at the occurrence of temperatures above 32 degrees C. In 2030. So you see the spatial pattern is interesting in that the southwest corner doesn't have much of this, as you might expect, closer to the oceans, but the emergence of increasing incidence of these higher temperatures coming into the northeast. Now, it's known already that these sorts of temperatures can be a crimp to yields for the northern grain belt. So this is a known issue, and this implies that as this keeps going, it'll start to become more apparent across these eastern margins, but starting to work its way down into a lot of the medium rainfall zones as well. So it's just a useful thing you can get out from this sort of exercise. And Meredith will probably be doing the same sort of thing, looking at chilling and frost events and those sorts of things. So it's just a bit of a shout out to the work that Meredith's been doing in this area, and I think that would make a very useful subject for a future talk. So it's just to show that you can really now getting tools to drill down to have a closer look at what it means for your part of the world. These are based on the older CMP5 models. The latest set are being prepared, but the results are not hugely dissimilar. So this is a thing that will be continuing to evolve, and they also take feedback if there's more things done that people want to see. So that's just an example of the tools that are now available. So I've probably talked a fair bit already, so I'll leave it open for questions at that point. And I'll hand it over to whoever's driving this show. So we need to get, I guess, questions from the floor, or floor and for people who've dialed in. I think yes. So the question for those who might know, yes, it's the question, yes. So that she's been doing stuff looking at frost frequency, and she's also doing work for other groups on various measures of chilling or cool temperatures. So yeah. So at the moment, the climate services for Ag1 just might give you you pick a temperature threshold, 2 degrees or something, and it'll give you some measure of that. It doesn't necessarily give you some of the more integrated measures as yet. But as far as those big picture things, yes, so I'm sure she's done stuff like that as well. So the frost frequency is an interesting one in that it persists for longer than people think. But it's a bit like the idea of a puddle drying out. It dries out from the edges first. So the areas that are frost central, like maybe Wandering or Corrigan or that sort of stuff, remain relatively frosty. But the areas that are a bit marginal, the frost instant changes quicker. So yeah, but she's probably got some good graphs on that one, so that we'll have to get her down to give a talk.
Another one to add to the list, Jane.
Yes.
No, it should be good at that. Yep, that'd be good.
Alrighty. Are there any other questions? I've just put a request on the chat to see if there's anybody. Are there any other questions?
Yeah, just going back to the map stuff. Meredith had put up change in rainfall. What's the gradient? I can't read this.
Sorry.
For the brown that's going from.
Oh, so this brown here. So that's 200 to 300 millimeters. Yeah. Okay. I should explain. The red bit there is 100 to 200 millimeters. So that's April to October. So the yellowy bit is 300 to 400 through there. So this main bit is, might have noticed a lot of ag in there. That rough figures is 200 to 300 millimeters as a seasonal total. Yeah.
Coverage and that gradient is going from.
Yes. Yeah. Well, see that again. That's just the compromises of what choices of the colour scales to map it. So the other possibility, you can actually chuck more in there, like you can maybe throw off some of the wetter scales and get more detail. Yeah. But she's got the numbers. So there is actually more spatial information in that brownie bit that's just hidden because of the choice of the colours for the mapping. So there's more stuff. Yep. But that's a good request, because you can do that on particular regions if you wanted to. You could look at the Corrigan Shire and for, or smaller regions, just pull out those. Yeah. Yep. So the beauty about that, she's got all of the data, and then within the R script, she can choose the region and choose the scaling. So yes, but that's a good point. That is a pretty broad brush approach, that one there.
Ian, do you have an online question from Rebecca D? I'm not sure what Rebecca's surname is. Rebecca would like to know if there is a map for expected cyclonic belt movements.
The cyclones, there's less consensus amongst them. I think there are some things in the reports on that one. One of the problems is the models haven't been giving consistent results, though in general they're actually expecting a decrease in tropical cyclone occurrence. And we have actually been observing that to an extent, though when they occur, their maximum intensity goes up. So there may be fewer of them, but they get nastier. Again, just the availability of more heat through sea surface temperatures and through the atmosphere makes the upper bound of these things go up. One of the problems with the climate models is the cyclones or the tropical cyclones are relatively small compared with the modelling scale of these things. So it's harder for them to resolve them. So that has been a bit of an issue. They have been getting a bit better with that. So that's still where they're not super definitive with that one. The models do better with the larger, like spatially larger weather systems like high pressure cells or cold fronts or those things. Tropical cyclones that might be 500 kilometres across, a bit harder to resolve. So that's an active area of work. And that was also looked at the IOC work as well. But they sort of said it was hard to pin the models down on this area, but they thought they would like to decrease a bit. So, and again, where it comes from to get the cyclone, you've got ocean temperatures, which means the potential for them will probably go up, but you then got to have the atmospheric convergence, and it's what that atmospheric patterns do on top of it that's less certain, and that's a bit that's causing the problem probably.
So we've had 2 questions in the room, so I'll take 2 questions online. So Lara, and I think it's Lara Fagan, wants to know, do the tools include wind chill as a factor and changes in wind movement?
I think at the moment for the climate services for ag, they don't have wind in, though the actual the greenhouse models will have wind as part of the things. So there are wind things there, but that just for that downscaling for climate services for ag, I think they're just doing temperature and rain to begin with, and it's one of those things they want to add more variables. In general, for us, if we see a continued southward shift or weakening or whatever the wintertime systems, we'll probably get less wind. If you get a more preponderance of weathers like this, clear sky days, wind speeds will decrease. And there has been some evidence over inland Australia of a decreasing wind speeds. That's what they call the great stilling, because observed evaporation rates have actually been going down over a lot of inland Australia rather than going up. So you might think, oh, it's getting hotter, evap goes up, but temperature is actually one of the least influential things on evaporation. So wind speeds have gone down in some areas, so evap's gone down. So yes, but that's a thing you need to know. And certainly the other inference, potentially if you get more difficult growing seasons, you may potentially get more soil exposed, and so there's a wind erosion concern is for that. So those questions have been asked. You can pull them out of the downscaled models, and there's active work to do with that. Yeah.
I have a question with the carbon, like, because a lot of the predictions, I don't know, for the new reports, if they take into account some form of mitigation, right? Like, because they are predicting for the end of the century.
Yep.
And
go back to this maybe. Shit.
Right.
Hold on. Go back. Should jump back and just get that one.
Yeah. So it is in the latest report on the 6th, do they mention that, how that would affect the trend? Like what we do between now and
well, see,
could we have like sharper declines on the projections if we actually do like global scale actions?
Could do. Yeah. I mean, each of those things, there's a whole story, there's a whole set of assumptions about what they mean with those shared socio-economic pathways. So that's, so there's a whole set of stuff behind that and what they mean in terms of global actions, whether it be technology changes and what they expect. Ultimately, it means the emissions into the atmosphere of CO2 have got to decrease, or CO2 and methane have got to decrease. As the budget stuff showed, it certainly helps to try and take it out of the atmosphere, that's fine, but it's a bit pointless if you're still sticking it up at a greater rate. And it's really this rate of change. It's the rate at which it's going out compares with the rate at which it declines. And what's left over, which remains in the atmosphere, is like the residual term between those two things. So it still comes down to, it's still like any air pollution issue, the most significant term is the rate at which you're putting stuff out in the atmosphere. It's always harder or less efficient to pull it out again. So that's really the thing, just don't put it up in the first place. That's still, from a budgeting point of view, that's still the most effective. So most of these things would come with them a substantial decline in the amount of carbon or greenhouse gas emissions. So that part of the budget would have to be hit very hard with those. So if you just try and it's nice to have vegetation, so revegetation, terrific idea, but don't expect it to save the world if you're still putting out 40 gigs of carbon each year. So it's not going to make the difference.
Yeah, which is the same idea of the soil carbon, the discussion of the soil carbon as well.
Yep. So there's lots of good reasons to. Yep. So there's lots of good reasons to do it, but it ain't gonna turn it around if that's the only bit you're going to do. So with all of these things, it's a whole package of measures. So it's not just one bit. But but they would all have to contain some restrictions in or actual reductions in greenhouse gas emissions. So the top one, it says no, you just burn everything. So that's what you end up with.
So I have quite a few questions online. Is there another question in the room, or I'll go back to online? Online. So, and I recognise one of our obligate surfing personalities in this question, Ian. Would you care to comment on coastal erosion, major swell events, and the possibility of rising sea levels, and what this might look for us?
Well, for the southern, no, this is where Iranian colleagues would be able to comment better on this for coastal. In principle, if you get cold fronts that are either less frequent or weaker, the coastal erosion events will probably decrease from that sort of driver. They'll still be there, but if you then add onto it the sea level rise, then you start to see events happening in areas that hadn't happened before. So you got sort of two competing drivers there, which would mean that if you had a higher sea level and a strong cold front came through, so the future doesn't say there won't be any, they'll just be not as frequent. So if you've got a biggie like the one we got earlier this week, but it's built on a higher sea level, then you'll get impacts hitting further inland than we'd seen before. And then people say, well, I've never seen this before. And that's what's happening in some bits of Eastern Australia with erosion events where they're built right up to the beach edge and cliff edge, and they're surprised when the house falls in the ocean, because that's what the landscapes do in that boundary. So, yeah. Yes, so from one point of view, yes, the decrease potentially in frequency or strength of cold fronts may decrease that part of it. But the sea level rise then just means the ability for these things to get inland goes up. But certainly Iranian Nick could do a more comprehensive, which might be another talk for them.
Could I ask another part to that question?
Question about the southern rangelands, and do we expect the climate to remain the same in that environment, or are there other more specific maps for rain and temperature in those zones.
The problem with the southern rangelands, it's sort of the boundary between, it's a bit of summer rain and a bit of winter rain, but it's not dominant in either. So for the south, it's more consistent because we're clearly a sort of winter dominant area, and for the north, it's clearer because it's a summer dominant area. So a lot of the southern rangelands, it's a mixture of both. And so the models in general would say you probably get a bit less winter rain in those areas, but with less confidence, and they might get more summer rain, but not as confident as you would say for the Kimberleys. So it's this grey area that's stuck in the middle. And we've seen, for example, happening recently that you've got events such as the cloud bands, which are relatively small-sized events, I guess, on a global scale that would have to be simulated because they can be very important, like they have at the moment. You've got stacks of rain throughout a lot of the southern rangelands. So those bits, that's an area that they don't do as well. So that's an area of actually of improvement to get a better idea. So the strongest confidence is really for the wet areas of the southwest and the far north.
Now, Steve M, and I think that's Steve May, is asking, do you have any view on the prospects for global scale temperature manipulation to bring down atmospheric temperature?
I presume if he means like some sort of terraforming idea, like people have proposed things such as, various things to make the planet more reflective, at different timescales and that sort of thing. They've tried that. Looking at the shape of the planet, if you were to make it more reflective, you only got a couple of options. One's to put a lot of aerosols up into the atmosphere, such as lots of volcanoes or set off nuclear bombs everywhere, which was the driver behind a few years ago the concern about nuclear winter. And there's lots of historical precedents of those sorts of, not so much nuclear winters, but large outbreaks of volcanicity driving cooling, such as Krakatoa, for example. Again, a lot of it's got to do with the scale, and you'd have to continue it. Like for example, Krakatoa made a couple of summers there in Europe much cooler, but then all those aerosols eventually got washed out. So in the scale of things, it was just a blip. And with those carbon budget or things, when you look at the actual currents of volcanoes, there's some really quite pronounced coolings from time to time, but they don't persist. So whatever's done in that respect, would have to have a large area to work. So if you just want to stick on the land, you're only doing 30% of the global planet. So you ideally have to try and make the oceans more reflective. So a lot of these things have been proposed. They're really, really hard, and they're probably harder than just trying to reduce the greenhouse gas emissions in the first place. So it's sort of like the idea of trying to have your cake and eat it too. But it usually doesn't work. Nature doesn't let you do that.
So, and I'm pretty sure it's Paul Galloway, is looking for rainfall change maps for the summer so that we can use them as tools to identify possibilities and resolve problems with our current future farming systems. Mm-hmm. That's possible? Yep, Meredith's got those. Well, she hasn't, she can generate them, so I'm quite happy to. Yep, no, but she has got a lot of info and mapping capabilities, so that would be, if she talks to Meredith, she's done a lot of that stuff already, so that'd be the best choice for that one.
What are you dubbing me in for?
When you want to go back online, and it's Richard F, and I'm not sure what Richard's surname is, but he is promoting the wine industry's climate atlas, which is forecasting weather conditions for 2100. Yep. And Richard wanted to know if the models in that align with this published work, whether your work aligns with this published work.
Probably will. Wine Australia did a lot of work with that, and they did a lot of multi-model runs. They would probably be the slightly older CMIP 5. So that was the models that were done of the 5th assessment report. The CMIP just stands for Coupled Model Intercomparison Project. Yeah. Climate loves a lot of acronyms. The CMIP 6 stuff is the latest things which they could repeat it with, but they won't give you a hugely different result than what they got before. Yeah. But at the time that when Wine Australia did it, they certainly would have used the latest models available. And they're presented as little frequency distributions and that sort of thing. So it is a really good guide, yeah.
Now, the chat is going off, and I'm trying to review it all through my phone, which is a little bit challenging. Now, Janet Conti is asking if there are discussions happening in relation to the impacts of climate change on regional development in the future. I would have said certainly yes.
Yep.
Yes.
Yep. Well, again, it's just part of various DPIRD projects going on.
And I do know that the development commissions have quite recently put in a climate strategy together.
Yeah, and see that's why like some of those downscale tools available can help regions have a closer look at what it means for their part of the world.
Now, Rebecca D, again, would any of these findings impact the forecast optimal areas for renewable energy across the state? And Rebecca is part of our regional development portion of the organisation.
Yeah. Well, certainly, I guess it depends what you're using. I mean, if you're using solar, we certainly get a lot of solar radiation scattered. So it's probably not going to affect that too much unless something happened that made it perennially more cloudy or that sort of thing. So we still have abundant opportunities for solar. For wind, in any event, they tend to have them in coastal or ocean areas as opposed to inland, because friction simply means the winds are often lighter inland compared with coastal or ocean areas. So it'll again, as far as I know, the wind turbines don't need massive amounts of winds to actually generate. So I suspect I'm sure they'll be looking at potential if there's persistent changes in wind maps for the placement of turbines. So I'm sure that's an active area of work. That's pretty obvious, but I would expect that barring some really strange changes in circulation, there'd still be sufficient resources if you're looking at wind and solar.
Yeah.
That sort of stuff. You've got geothermal, because that's moved around a bit. That's still there.
Yeah.
So yeah, so I'd say that's still okay.
Now, the only other question I can see in here is, I think for Richard with the wine atlas, but there is a question here about direct incentives and investment for Australian primary industries at regional level, i.e. which livestock is better for which soil and climate types, what minimum quality forage. And there is another response here that the Sheep Links project is looking at that.
Yep, that's the stuff that Meredith is also contributing to as well. Yep. Yep.
So I do believe, unless there's any more questions in the room, but thank you very much.
Very good. Thank you for your attendance. Thank you all. Thank you.